daily, and eventually the daily are collapsed into monthly ones. As I point out on this slide, timely, statistically efficient updates of forecasts are essential for a vast array of disciplines involving public policy planners, financial executives, even gamblers, and the list goes on. And that is why this research topic is rather popular. The focus of our study is to assess the relative predictive accuracy of alternative mixed frequency forecasting methods within the context of forecasting Philippine inflation, GDP growth, and other related macroeconomic variables. By now, all the methods that we consider are commonly used in current econometric forecasting environments, but new variations keep sprouting as new needs, new data types emerge. Also, there are some local research activities in the Philippines that deal with this topic as well. And in particular, I know Dennis Mapa has been working on mixed frequency VAR or vector autoregressive processes applied to Philippine nowcasting. The paper focuses on variations of mixed frequency dynamic latent factor models, or DFM for short, and described quickly on the left side of the slide. And on the right side, MIDAS, an acronym for Mixed Data Sampling Regressions. For now, suppose we have only monthly and quarterly data in our sample, and in your mind, stack each variable data into a column of monthly observations so that quarterly variables like GDP and PGDP have missing observations in their columns. The first 2 months of each quarter is a blank. If all data are available, estimation and simulation of the two models have already been around for a long while. Kalman filtering in the state space formulation in the case of DFMs. But complications arise when, as in our case, some observations are periodically missing. DFM and MIDAS deal with this problem of missing observations in the mixed frequency data set in two different fashions, as we will see in the succeeding slides. In the dynamic latent factor model, the underlying philosophy is that macroeconomic fluctuations are driven by a small number of unobserved common shocks or factors and an idiosyncratic component peculiar to each economic time series, dependent on observed exogenous variables, W in the equation, in the measurement equation, and unobserved specific errors, epsilon t. Capital F represents the unobserved common shocks in these measurement equations. The second group of equations that make up the basic state space model explains the behavior of the unobserved common factors. The state equations would require an additional term in the specification, as we see on the slide, if we allow possible interactions with other observable indicators, which would require a second term involving W or some other exogenous variables in the state equations. As specified, the basic model cannot be used directly for estimation purposes because of the missing observations in capital Y and possibly W, the exogenous variables, namely those that are quarterly, given that this is a monthly model. This is addressed by deriving an expanded operational state space model in monthly terms without any blanks at the measurement equations. Another alternative variation for the dynamic factor model arises when there's a large number of indicator variables. Later on in our summary tables, we call this dynamic factor large. just to distinguish it from the basic dynamic factor model. And the main idea behind it is to reduce the dimension of the indicator variables through factor analysis, then deal with the dynamics in the behavior of the latent factors, that's in the second equation for a capital F, which by then will be observable, and finally model the impact of the factors on the target variables. That's the third equation, set of equations for capital Y. MIDAS, if you take a look at the model equations, on the other hand, takes on a completely different approach and estimates a reduced, what econometricians would call a reduced form model, a monthly regression of each target variable on monthly and possibly quarterly indicators using parsimonious distributed lags to represent missing observations. So very briefly, a stylistic way of describing this would be to write it as in the slide, where the contemporaneous observation on Y, on the target variable, depends on contemporaneous values of W, the exogenous explanatory variables, as well as lagged values. In order to economize on the parameters and have a parsimonious parametrization, restrictions in form and values are imposed. And these are various distributed lag structures that have been used. Unrestricted step function, so-called Almond polynomial lags, exponential Almond, as well as beta distribution. There are also other variations in MIDAS to take care of additional parts. For example, if you look at this specification here in the model equation, there is no variation in lag, there is no lag values of Y showing up. And so one way of doing that is through MIDAS var, where you essentially introduce lag values of Y as well. In case of factor MIDAS, the idea is to utilize factors before doing the MIDAS regression. In principal components, as the term denotes, the initial list of indicators is collapsed into principal components utilizing stepwise regression as a selection process for determining, for choosing the principal components. And in our particular case, both contemporaneous as well as lagged principal components are introduced and taken into account in the selection process. Autoregressive distributed lags, here, the dependent and explanatory variables are related not only at the current period, but at cross-lag values up to a certain order. In our case, we restricted that to 1 for the dependent variables and to 12 for X. We also, in addition to all these different variations of MIDAS and DFM, we also consider combination of forecasts as a way of achieving or improving forecast accuracy. And the different schemes that, weighting schemes to do forecast averaging that we considered are listed here. There are 5 of them. One is to use the mean of the forecasts coming from the different methods as the combined forecast. A second one is median. And the second, in terms of the weights, use the mean square errors for each of the forecasting procedures. And then the ranks based on the mean square error. And last, and that this will turn out to be the best one among the 5, is to use weights coming from least squares regression of actual observations for each of the target variables on forecasts at time t. So what did we do to, what was the approach that we used for our methodology? First, we estimate the forecasting methods in the comparison pool that we would be analyzing and calculate forecast errors over the sample period. The sample period in our case is 1999 to 2019. Results are discussed here all pertain to one period ahead for forecasts. And we first compare forecast performance measures. In our case, we rely mostly on mean absolute error. No need to take percentages because of the fact that all our target variables are expressed in terms of growth rates. Then we apply statistical tests of comparative predictive accuracy, the Diebold-Mariano test, of course, and an extension of the Diebold-Mariano test, the Mariano-Prevet test. The Diebold-Mariano test compares two forecasting methods and tests for the equality of forecast accuracy of two forecasting methods, mano a mano. And it's based on the sample mean of observed loss differentials. But in our case, we use the squared error loss, but the procedure itself is very flexible and can be used for other specifications instead of squared error loss. And it is analogous to the classical test for equality of two means, except that in this case, we have to deal with heteroscedasticity and autocorrelation in the observations that are being used. The Mariano-Prevet test compares more than two forecasting methods. And as you would expect, it would be an analog of the classical multivariate test for the equality of K means. In the next slide, we talk about another type of tests that we utilize, and this is the test for forecast encompassing. And here, given a set of forecasting methods, we want to test the null hypothesis that a particular method, say call it forecast J, contains all the information in the other forecasts. And this is what the forecast encompassing test does. And the test is based on a regression of forecast errors of the particular method of the other forecast in the pool. And the null hypothesis is accepted if all slope coefficients in these regressions are insignificant. To implement all these procedures, the estimation, the calculation of error measures, accuracy measures, and the application of the tests, the econometric statistical package used was eViews 11, the 2019 version, and a recent R package for calculating the Mariano-Prevet test for the multivariate test. Before going to the main findings, let me just briefly point out that the database includes daily, monthly, quarterly data over the period 1999, month 1, to 2019, month 12. The target variables that are forecasted, all in terms of year-on-year growth rates, are real GDP and the GDP implicit price deflator. I just call it PGDP in my discussion. And these two are available on a quarterly basis. And monthly data available for the other four targets, the Consumer Price Index, CPI, which is the basis for our measure for inflation. And then the Industrial Production Index, Merchandise Exports, and Producer Price Index. Real GDP, industrial production, and merchandise exports are obviously real sector variables, while the other remaining three, the CPI, the PGDP, and the PPI, are all price variables. indicator variables that we utilize, the W variables in my earlier notation, are nearly 60 indicator variables, both coming from Philippine data as well as external data. And here are the 7 blocks that you can categorize them. The external prices in particular deal with, our prices in the world, in the US, as well as the Dubai oil import price, and other external data that are relevant to Philippine growth and inflation are the OECD leading indicators, uncertainty index, and the world trade volume. We also utilize, note that we also utilize expectation survey data that come from the Bangko Sentral ng Pilipinas. The 2 main data sources that we use for the Philippines are the PSA, the Philippine Statistics Authority, and the Central Bank of the Philippines. And for the external sources, the Federal Reserve Board FRED database of the Federal Bank of St. Louis and the Bureau of Labor Statistics, and IMF and OECD. There are quite a few findings, but in the interest of time, I'll just focus on 2 main findings. One is on the results of the methods, on the encompassing tests that determine whether there are forecasting methods that will encompass all the rest of all those that we are comparing. And it turns out that factor MIDAS encompasses the other 10 or so different procedures that we compared for GDP and the GDP deflator, the 2 quarterly data, target variables. None encompasses the others in the case of industrial production and merchandise imports. While for CPI, it is the DFM and DFM large that would encompass the rest. And for PPI, the stepwise and bridge. And when we look at this chart, a little bit confusing, but the different lines pertain to each individual forecasting method, connecting the MAE, the mean absolute error values for each of the 6 target variables. All the lines, apart from the big blue line, let me just say that for the purple one, the purple line, connected lines pertain to factor MIDAS, and the big red pertain to the dynamic factor model. And the big blue line is another special one, but does not belong to this individual group, but is a combined and the least based on least squares weights. So what we see is that there's a lot of crisscrossing lines for the individual forecasts, showing that there is no clear winner. What we're plotting here are mean absolute errors, and so the lower the values, the better. Ideally, what you would like to see is one individual procedure dominating everybody else by being uniformly lower, but none is. It just goes to show you that there is no clear winner among the individual ones, and leads to the likelihood of being able to attain some improvement, and in some cases vast improvement in forecast accuracy by doing a combination. And it turns out that when we compare the 5 different schemes for forecast averaging that we mentioned earlier, the use of least square weights turns out to be the best. And it showed lowest MAE for 5 of the 6 target variables and second lowest MAE. And that is this blue line here. So what we conclude from just these comparisons and these calculations is that there's no clear winner, and just about every method considered performs better in some cases and worse in other cases. And so one likely way to proceed is to combine the forecast, and in that process, utilize the least square weights because they perform better than the others. As always, in doing empirical comparisons on projects like this, you always end up with a lot of questions, and there's no end to it. And let me just quickly go through this list and just point out some of the questions that arise as I try to get some clarity in looking at the comparative merits of these alternative procedures. We should take a closer look at the magnitudes of the forecast errors and ask ourselves, will this be good enough for real life situations, like for an inflation targeting program? Which indicators are useful? Are the magnitudes big enough to give you a reasonable range to set your inflation targets? There's also the question of multi-period forecasting horizons. There are further enhancements in forecasting model specification, time dynamics, including additional explanatory variables, using self-rated poverty happiness indexes like as in SWS. They could prove very useful, as we seem to find in some recent projects. And how about other big data? Using daily data more directly in nowcasting is also important. And to explore the potential to quantify impact of big sudden shocks in the system, like what we're now facing in COVID. With all these questions and issues, let me end here and leave some room for questions later on. Thank you very much, Arniel.
Thank you very much, sir. From one theme of statistical science, we will move on to an entirely different spectrum of statistical science. Please reserve all your questions for the Q&A after the talk of the next speaker, or alternatively, you can type your questions in the Q&A box. We will read it later on. So our next speaker started from UP Los Baños for his BS and MS statistics degrees. He then proceeded to pursue MS and PhD statistics at Florida State University under the supervision of Miles Hollander. He is currently professor at the Department of Statistics, University of South Carolina. He also served Bowling Green State University and has visited University of Michigan. He's a fellow of American Statistical Association, elected member of ISI, and current vice president of PAASE. Quick trivia for our users here. He actually contributed the packages GCMREC, SURVREC, and GVLMA. Maybe there are additional packages now as he delivers his talk. He will talk about Poisson and over-dispersed Poisson regression models with application in forecasting COVID-19 death. So by the way, he just updated his slides early this morning to account for the recent data on COVID deaths. Please welcome Professor Edsel Pena.
Thank you, Arniel. Do you see my slides?
Yes.
You can see it. Okay. So thank you very much, and thank you, of course, for Gisela, her tireless effort in organizing this symposium conference during this pandemic. It's very admirable, and it's nice that we could see everybody in the statistics community who are in Europe, the US, in the Philippines, and I've heard a lot of the other people there. Dr. Mariano, Pilino Lancigan was my professor, Ani Runelia was my advisor in Los Baños, and then Grace and I were together in Bowling Green State University before we left Bowling Green. So And of course, Herniel, I know from UP Diliman. So my talk actually is not too complicated. It's actually quite simple. And this actually started when the pandemic started. I was teaching an undergraduate engineering class in statistics. And then I was also teaching a graduate class in stochastic processes. And because of course we all had to do things online, I started using this as a motivation. Every class meeting, I update the data and I pose the statistical question. I say, how could you predict how many deaths is going to be 15 days from now? Something like that. So of course, in the beginning, it's very difficult to do that because you don't have much data. But as time passes by, the simple methods that we were using was not working well at all. They were not working because they're too simplistic. And so it became a challenge to me. I said, how do you do this? And Ben Lieberman was a student in my stochastic process class, and I was teaching them the continuous time Markov chain. And that is one possible model, compartment models. And then George Sluta is a professor at Georgetown. I met him in January when I gave a talk in Georgetown. And he said, let's collaborate on something. And then the pandemic hit, so we decided that we should collaborate on something about the pandemic. And then Taeho Kim was my former PhD student. He's now a postdoc at University of Haifa in Israel. And so we gathered together online. We didn't meet at all, of course, for the past 3 to 4 months. And then we ended up with this paper. And we deposited the paper in the archive 2 weeks ago, or maybe 1.5 weeks ago. So it's the one that is contained in the bottom part there. So you could easily search that. Okay, but here's the motivation. So the European CDC, that's the European Center for Disease Control, publishes this data updated every day. This is for all the countries in the world, okay? It publishes the number of cases, the number of deaths daily, as well as cumulative. And so here, for instance, I put the one for USA, and this is until July 18th, when I first completed a version of the paper. The left plot there is the daily deaths. Okay, so this is the daily deaths, and you notice, of course, that things are increasing again by 7/18, and that could be because of the social easing that was happening. And then on the right plot here, that is the cumulative deaths. As time passes by, it's the cumulative deaths. So here, looking at this picture, for instance, you could ask, what will be the total number of deaths in the USA by August 1, based on this data that we are seeing? How do we do that prediction? So that's the basic motivation. And you could do that for many countries that you're interested. In particular, for instance, this is the data for the Philippines. And you notice for the Philippines, there's this big outlier which could mess up potentially whatever you do in prediction. Okay, so the program that we have, you could pick any country and then you could actually do that. So but that's the basic motivation that we have. So the question then is, given this type of data, if I wanted to predict or to forecast the number of deaths, total deaths at a certain time, how do I proceed to do that? Okay, so that's the basic motivation. And why is that important? Because it's important, of course, because it could decide whether we should go back to social distancing. It could decide whether we should open universities or school this fall. It could decide whether beaches and the businesses should be open or closed. So these are very important ones. It could decide the election in the US, for instance. Okay, and but it also leads us to some very interesting statistical questions that are outside of the pandemic that could be utilized in economics, in physics, for instance, in geophysical studies like the ones that I listened to the other day about earthquakes in volcano eruptions. Okay, another thing is that we'd like science to be believed by people. And if the forecasts that we are providing to society are bad forecasts, then the belief or the trust on us will start eroding. They will say, why should we believe you? Your forecast was quite bad a month ago, something like that. So it's a very important issue that we have to consider. Now, when you think about this problem, I said, how do I explain this? You actually have to start thinking about a very simple experiment. In this the experiment of tossing a coin. You might say, how is this pandemic related to tossing a coin? Okay, and here's the idea. Let's imagine that you have a biased coin and the probability of landing up head is equal to theta. If you toss this coin n times, and then you denote by y the number of times that the head occurred, then we know from basic statistics that y has a binomial distribution with parameter n and theta. So the mean is n theta, the variance is n theta times 1 minus theta. Okay, so this is what we know from our very basic statistics. Okay, the standard deviation is the square root. Okay, now, so here are three shapes of binomial probabilities. I think the first one is a 50-50 chance. The second one is a 30% chance for heads. And then the last one is 10% chance for heads. And you notice that it gets shifted and then you get some skewness as you move to lower probabilities of header. Okay. Now, one of the things that we study from statistical theory is that if you let n, number of trials increase, but you also let theta n, the probability of a head, decrease, but you keep the mean the same as you change n. So you set that to be equal to lambda. And then you let n go to infinity for this binomial probability. It will converge to what we call as the Poisson probabilities. Okay, so, and these probabilities here are what we call as the Poisson probabilities. And what we have done there is to let theta sub n go to 0. So technically, the probability of an event, which in this case is head, is going down to 0. So it becomes rare. So as a consequence, these Poisson probabilities are models for what we call as rare events. Okay, and here's the basic definition of a Poisson probability function. Okay, so I'll denote it as PUI lambda. In the lambda is the rate, which is the mean, and it is also the variance. So the standard deviation is equal to the square root of lambda. So it's a very, very important probability function, but that's simply coming from the binomial distribution as a limit. Okay, and here are three shapes that I put here for the Poisson probability function. The first one is when lambda is 0.5, so you have very high skewness. The second one is for lambda is equal to 10, and then the next one is for lambda is equal to 30. And we have here from the central limit theorem that if you let lambda increase, if lambda is large, then you actually have an approximate normal distribution. And that's coming from the central limit theorem. Now, the Poisson model is very important because it models general rare events, earthquakes, volcanic eruptions, house fires, vehicular accidents, fights between husband and wife. That's also a Poisson distributed random variable. Getting a perfect score in standardized tests, assuming that there's no cheating going on there, that's going to be a Poisson distributed thing. Winning a lottery, that's a rare event. Getting a paper accepted for publication, that's a rare event too. And of course, getting infected by the SARS-CoV-2 virus and dying from COVID-19. These are rare events. And as a consequence of that, the Poisson distribution is a good model for these rare events. That's why somehow the Poisson must come into the picture when we are trying to analyze these COVID-19 deaths, okay? Now, so the basic problem that comes up then is this. I have to start with. Let's suppose that I have a random variable that has a Poisson distribution with parameter lambda, okay? What you would like to come up with is a subset of the set of integers, I'll denote that by gamma, such that the probability that y sub 0 belongs to that subset is at least equal to 1 minus alpha. I'm assuming for the moment that lambda is known. If you have that subset, okay, then you would call that subset as a 100 times 1 minus alpha percent prediction region. Okay, it's like the prediction region that we have in normal models, okay? But here you are dealing with a Poisson random variable, okay? Now, of course, if you have a prediction region with a certain prediction level, like 95%, you would like it to be as small as possible, okay? Because large prediction regions will be useless to us. It doesn't tell us much information. So you have to set your level, and then you want to make it as small as possible. So that's what we would like. Now, why do we want prediction regions? It's because if you simply give point predictions, like you say, the number of deaths is going to be equal to 100,000. You know that that prediction is not going to be right. You could never be 100% correct about that. So what we would like to do is to have a degree of confidence on that region, the amount of size of that prediction region. That's why prediction regions are more useful than point predictions, because it provides us the degree of precision as well as the accuracy of the forecast that we are providing. Okay, but we would like that to be as small as possible for a given level. Okay, now when lambda is known, okay, you could actually obtain the very best prediction region that you could have. Okay, and this is given by this weird looking formula. Okay, it's the union of several sets, but the basic idea there is actually the idea behind the Niemann-Person lemma in hypothesis testing. You could use the calculus of variations to come up with the shortest prediction region that you could have for a given level of confidence, and that is provided by this. And that's not very difficult to compute, but what I want you to see here is how you actually obtain that. And the basic idea is this. If you have the Poisson probability function that is provided by this plot here, what you're basically doing is you're cutting it at a certain level, okay? And you cut it at a certain level such that the probability inside here is close to that confidence level that you would like. So if you wanted 95% confidence level, you set that such that this total probability is 0.95. Of course, sometimes you have to do randomization to get exactly the 95% level. Like in the Niemann-Person lemma, you usually have that gamma, which is the randomization. And that's provided by this part here. But basically, when the lambda is large, that randomization is not very critical. But this is the picture of how you obtain the best prediction region that you could have, okay? Another way that you could do that, and I think this might be familiar to many of us, is simply to use the normal approximation. Y sub 0 is approximately normal with mean lambda and variance lambda. So you could standardize and you get this approximate standard normal. You could then use this as a pivot for Y of 0. And then when you do that, you obtain this prediction region. Okay, but that is when lambda is known. Okay, now that's not the important one though, because the important one is the situation when lambda is not known. Okay, so how do we deal with it? Okay, now if you don't know lambda, then you must have a way of estimating lambda. So what we do here then is we assume that we have a random sample or training data, y1, y2 up to yn, that came from that Poisson distribution. And then the goal is to construct prediction region for an unobserved y0 that also has a Poisson distribution with parameter lambda. How do you do that? So the idea is very simple. You say, okay, I'm going to observe y1 to yn. I could then estimate lambda. And then having estimated lambda, I could plug that estimate into that prediction interval that I presented when lambda is known. How do you estimate lambda? You could use maximum likelihood, or you could use method of moments, and that simply leads you to the sample mean as the estimate of lambda. So this is your estimate of lambda. And then, as I've said, the intuitive thing to do then is you say, I'm going to plug in that lambda into lambda on these two prediction regions. And I say, oh, that's quite intuitive and reasonable. And I say, isn't that? Okay. The problem though is that it is actually a faulty strategy. Why is that faulty? Because if you simply plug in this lambda hat into these prediction regions, you did not take into consideration the induced variability in the estimation of lambda. So what you will get is, if you simply do that, you will get narrow intervals instead of proper intervals. So if you get narrower intervals than what you should have, then the confidence coefficient that you had set, like a 95% confidence, will actually be lower. And so you are not satisfying the guarantee that you are providing your users. So you have to do something else, okay? And how do you do that? So what you need to do then is to try to correct for the estimation of lambda And there are several strategies. I'll mention here 2 ways. One of them is to use a second order Taylor expansion, and then to adjust the PK after you had estimated it by lambda. And this is one way. The other way is to simply use a normal approximation, but to take into consideration that you had estimated lambda. And what you have to do there is to use the delta method. And when you do that, you obtain this prediction interval, okay? So again, this still looks familiar, okay? Because of the correction there, okay? This one is a little bit more complicated. And in fact, this one did not turn as well as this one for large lambda. But these are ways of doing that. And you could examine the performance of these different prediction regions. And here actually the 3 that I mentioned will be the black one, the blue one, and then gamma 3, which is the pink one, okay? And these are the level for different sample sizes and for lambda equal to 5 here. And I think the gamma 1 there is the one that is based on the normal approximation. That seems to perform best in this situation. And then the second plot here pertains to the width of these prediction intervals. You would like that to be short. The black one, which is the one based on the exact prediction interval, where you simply replace lambda by lambda hat, has the best length, except that it suffers in terms of the confidence coefficient, because I didn't adjust for the estimation of lambda. But basically, the one based on the normal approximation ended up best in that type of situation. Okay, now that's the situation, and this is for n lambda is equal to 30, same type of conclusion. Now, that's the situation though, where I only have one Poisson distribution, okay? I only have one lambda. That's not the situation when we are dealing with a pandemic, because for the pandemic, what you actually see are the deaths, daily deaths for different days, okay? Like the picture that I have shown here, this is the data that we are seeing. So it's not right to assume that they have all the same parameters. So how do you deal with that then, okay? So the way we dealt with that is that we used the number of days since the beginning, which is 1231, as D, variable D. And then we also categorized that day into 0, 1 to up to Sunday, depending on what day that is. And what we assume then is that the number of deaths, daily deaths on day D, has a Poisson distribution with rate that depends on that D in the day. Okay, and so this is the model that we are considering, and this is what you call as a Poisson regression model. Okay, as compared to the earlier one, we have now here prediction, predictors, and you call this as the Poisson regression model. Okay, and the K there is the order. Okay, so it's a polynomial basically, but you could use some other basis function for this one. Okay, so you have this situation. Okay, I think that was my timer, but I might have. Okay, so now, so you have this data, and then you fit that then, okay, and you could do the fit for. You could estimate the theta parameter, which are the coefficients, using maximum likelihood, okay? And then from maximum likelihood theory, we know that the estimator is going to be asymptotically normal with mean theta and then the inverse of the Fisher information, okay? Fisher information is the negative second partial derivatives of the log likelihood, okay? And as a consequence, if I wanted to predict the value of daily deaths at T0, a future day, okay, I could use again the idea that I had earlier, but now in a more complicated fashion. Again, I'm going to use the delta method, and then when I use the delta method, I come up with this prediction region or interval. Actually, you could just remove that, and then that is a prediction interval. Okay, so it's much more complicated because of course you have matrices now here, but the principle is the same. That's how I presented the case without the covariates. Now, so I said, let's apply this idea then to the COVID data. And then this is an application for, I think, until May 15th, when we were in the middle of this research. And so we apply this prediction region. But then what you would notice for this prediction region is that there are still a lot of points that are outside. That shows somehow that the model is not right, that there is over-dispersion. Because if the model was correct, there shouldn't be many points outside of these prediction regions, okay? So we knew that something went wrong, and I was very concerned about that because I was showing this, I said, this model is not working properly. So we have over-dispersion. So why could there be over-dispersion? It could be because the reported daily deaths are getting perturbed, okay? There could be lack of personal or certain days. So consequently, people are not there to report things. It could be that the definition of what COVID-19 death really means, so it keeps changing. It could be gaming of the system. It could be excess deaths due to other causes, or maybe causes that are not getting attributed to COVID-19. And of course, as just the other day had mentioned, all models are wrong, but some are useful, okay? So what we did then is we said, what could we do to correct for this over-dispersion? And it's not technically over-dispersion at the point zero. It's usually zero-inflated models. It's not that way. So I keep thinking about this, and it turns out that we could borrow an idea from survival analysis, frailty models. And what you basically do is you assume that you have an underlying hidden process, which is Poisson, okay, that's the Y star. And then you have a latent variable, CD, which you don't observe, okay, that has a gamma distribution with scale parameter and shape parameter psi. So the mean is 1, and then the variance is 1 over psi. And then you assume that these are independent, okay? And then the observed process, the one that you are seeing, is a perturbation of that Poisson variable perturbed by the CD, and then you take the integer because you have integer values here, okay? So now, when you do that, you actually get an over-dispersed model. The mean is still approximately the same as the original, but the variance is now larger than under the usual Poisson regression model. In the Poisson regression model obtains when you let psi go to infinity. So you have a bigger model here then, with a Poisson regression model obtained as a limiting model in this situation. So this is the basic framework for that, okay? And you could then estimate theta psi using C estimation. It's hard to do the maximum likelihood because you don't have a closed form. So you could use C estimation or M estimation. And then you also have the Curie for this, okay? And here you get what you call as a sandwich estimator because you're not technically using the MLE. But this sigma is still the Fisher information in that situation, okay? But this need not only simplify to sigma inverse. And you could estimate this covariance matrix consistently, okay? Now, because of that asymptotic, okay, you could then come up with a pivotal quantity again for Y0. And then this is the pivotal quantity. From this pivotal quantity, I could then flip that to come up with a prediction region, approximate prediction region for the number of daily deaths at D0, and that is given by this, okay? It looks complicated, but it's not really that complicated. There's some inversion that needs to be done here, so that's where the computational thing comes up. But it's kind of still simple, following the principle that I had earlier. So we apply this to that data that I had earlier, and then how you notice that the prediction interval actually covers the observed points, okay, as compared to earlier when it wasn't covering many of the points there. So somehow this tells us that this is okay. And then the degree that we used here is 5. So 5-degree polynomial with respect to the day number, and then of course the day also was there. And that the data was until May 15, okay? Now, but predicting the number of deaths per day is not the most important one. We would like the cumulative deaths. So how do we do that, okay? So why is this important? Because this could impact behavior. If the cumulative deaths is increasing too quickly, people might say, I'd better wear a mask. Maybe Trump will suddenly decide that he should wear a mask. People could decide who to vote because of the number of people that are dying, for instance, okay? And so the idea that we had done here, although I could now improve this today, but I will stick with this. The idea is that if it is today, what you could do is to predict the number of daily deaths for the days that are coming forward, create the intervals there, and then simply add the lower bounds, simply add the upper bounds for those, and then overall you get a total And when you do that, that provides you a confident, conservative prediction interval for the day that you are interested. It's conservative because you might be interested in 95% prediction interval, but you are actually getting 99%. So you're sacrificing a lot, but at least you are guaranteed that you are obtaining the correct interval, okay? So that's the basic idea. But today, or actually this week, we got an improvement over this that gets us another one because we didn't use this CDAC corrected ones. We obtained a more direct one, but it's not covering that in there. Now, so these are now plots only, so I'll be done in 1 minute here. So this is the application to the COVID data. And then this is from, I used the data until July 5. And I'm predicting until July 20. I think this is when I started preparing the slides. So the data that I used is up to here. And then the red ones there were the subsequent observations. So you notice that the prediction interval covered almost all these points. Actually, it covered all the succeeding observations. Okay, so everything seems to be fine. And then this is for the cumulative ones. For the cumulative ones, you notice that there was degradation at the end, and I think that was because of the social easing, so that the model, the data that I used did not take into consideration. But you notice that it's still quite good in this prediction interval at 720. So because I was looking for today, I look at the prediction for August 1 using data up to July 15. And then this is the data is here. These red dots here are the predicted daily deaths. You notice that they're quite good actually in terms of the fitted prediction curve there, and so on and so forth. You might say, why is this wiggly? Because the day effect is actually significant, okay? The highest daily deaths that are getting reported are on Tuesdays, Wednesdays, and Thursday. And that's quite puzzling. But what happens that on Sundays, in Saturdays, people I think are not in the hospital, so they do not report as many deaths as they could. Okay, but that was significant, and that's why you have this wiggly thing here. And then for the cumulative deaths here, you notice that from 715, these are the subsequent observations. The blue line there is the predicted curve. So almost all the points there are very close to the predicted curve, but of course, the prediction interval becomes wider and wider as you go farther and farther away. And today, so what I did is, that's the one that Ernil was mentioning. I run it today, so the last pointer is 726. And then I also did, what's the prediction if I use all the data until today and until August 1. And then these are the no red curves there, points, because I don't have those data yet. But that's the predicted curve there. And then this is the predicted for the cumulative. Okay, notice that, of course, since I'm closer to August 1, you have another prediction interval. Okay, so it seems to be working. What we have to see, there are still problems, especially when you want to do long predictions. So there's my concluding remarks. I only use daily deaths here, okay? Why not other feature variables? Okay, so you could, but you have to be careful also there. Why not a longer forecasting horizon? And you recall Donald Rumsfeld, known knowns, known unknowns, unknown knowns, unknown unknowns. So you could have adjusted numbers, social distancing, easing, all these other things that could have an impact on the data. And then there's also the feedback loop. Whatever the government does, it could affect the consequent number of deaths later, okay? And then of course, there's the problem of extrapolation, okay? I say actually that COVID-19 deaths forecasting is as dangerous as the disease if you're a statistician. And then I mentioned, of course, Niels Bohr. He said that it is difficult to make predictions, especially about the future. And in this COVID forecasting, you immediately know in a few days if your forecasts are good or bad. Okay, and that ends it. And just wanted to thank again Gisela for her really tireless effort in organizing this. Ernil for inviting me to his session. I get to meet other statisticians. And of course, it's very nice to see Grace Montepiedra. I think I saw her last in 1996 maybe, and so on. And to all the people that are here, thanks for listening. So I might have exceeded time, Ernil. Thank you.
Okay, thank you very much, Edsel, for the very interesting talk. Now, we will have the first part of the Q&A. So again, please type your answer in the Q&A box. If you have similar questions to what is already typed there, you can upvote so it can be prioritized. Pa will also be monitoring people from watching at the YouTube live streaming. So if you have questions there, we can also entertain those. All right. So there is first question here in Q&A box from Hill Mendoza. For Dr. Mariano, sir.
Okay.
It says, I am not an econometrician, but perhaps I can consider myself as an applied user of econometrics. So my question may not make sense. Please pick up what you think is relevant. I have a few questions, but each one I think can be quickly answered by Dr. Mariano. Why are packages, what are packages did you use? Can you share them? Did you develop your own codes in R? Are they open source and can share them? Now to my theoretical questions. You presented different models to forecast GDP, growth and inflation. I am particularly interested in the mixed frequency approach, DFM and MIDAS. Which model performs best in projecting GDP growth and inflation? GDP price deflator? Yes, sir.
Okay. I'll let Suleiman answer the questions on the software and the packages used. Let me go to the theoretical question of which forecasting method for which variables. In one of my slides, I pointed out that the DFM and the DFM large will tend to encompass the other methods and therefore dominate the other methods in that sense when dealing with CPI, with inflation. But for GDP and the GDP price deflator, what happened here?
Yeah, we hear you, Bobby.
You
can keep on going.
I'll just keep on going. For the GDP and the GDP deflator, the encompassing test that dominates the others would be MIDAS. Suleiman, your comments about the software that were used.
Yeah, the software, we basically use eViews 11. So that's 11. And for the R package, for the multiple Diebold Mariano test or Mariano Preve, is the R package called MultDM. So MULTDM, that's the R package that is available on our website. eViews is owned by IHS Market. So you have to purchase the software for eViews. So that package includes most of the methods that we have in the paper.
Okay. Okay, sir. Okay, so Hill Mendoza says, thanks. Okay, so we will now move on to the next question from Mike Lucagbo for Dr. Pena. In modeling the lambda, how about using covariates such as hospital beds, cases in the previous day, intervention effect due to policy, instead of or in addition to just the next day index? I have similar question, Edsel.
Yeah, then that's a very important question, actually. The problem there is this. Let's say that we are trying to predict 15 days from now, okay? And let's say that we had incorporated in the model the number of beds on the day. But that might not be available when we are on the day that we are predicting, okay? Like one of the things, of course, that we thought about is to use cases, the number of cases, because that could be informative. But then if you are trying to make predictions 15 days or 30 days ahead of time, we wouldn't have that information for that particular day. So unless we assume certain things, we could actually estimate them and then put a data there, the estimator. But the other problem that we were kind of troubled with is that when we think about the data that are being provided, the number of cases is very unreliable. Even now, I think it's very unreliable. So we said, let's just completely use the data that we think is reliable, and that is the daily deaths that couldn't be cheated on somehow. But the cases could be altered and so on and so forth. So it could also be affected by the number of tests that are being performed. So consequently, it might throw up the model. So the idea that we had is, let's just make it as data dependent with good data that we have we thought that the daily deaths data was the most reliable in that context. You could also use some other things, like you could use the infection rate or the transmission rate or not, and then put that into the model. But then you have to have data to try to estimate that properly. I think a continuous time Markov chain model might perform better, okay, as compared to this, but then you have issues of estimating those parameters in the data might not be there. So we wanted this to be as simple as possible with just the minimum data in the data that we use, just the daily deaths, okay? So that's the reason why we did that. And certainly you could use some other predictors like was social easing introduced? You could put an indicator variable there, but we didn't do that in this case, but you could certainly do that. In terms of the software, because I think somebody was asking, in estimating the data parameter, you could use GLM, and then with the family Poisson, and then the link is log. You could use that. But in the over-dispersed Poisson, you have to create a new function to estimate the psi, and then to estimate the covariance function, and that's the programming part. We have that. We haven't put that yet in terms of a package. We are planning to do that or to release it, but we used R. Okay, so in that situation, the plotting was I wrote all the codes on it. It's kind of fun to write codes. Okay, so it sharpens you somehow.
So you're already answering Gil Mendoza's question.
Yeah, I saw Gil.
Yeah.
Question there. Yeah.
Okay.
Yeah.
All right.
Erniel?
Yes, sir.
This is Bobby Mariano. Can I ask a quick question with Edsel?
Yes, sir.
Yeah.
Or are you running out of time?
It's okay, sir. We still have a few minutes.
Okay, one quick question to Edsel. Edsel, if you look at the pattern of deaths, pataas ng pataas, ano?
Yep.
So the procedure for your confidence, your prediction region is always increasing. What I'd like to see is, when can we make it go down?
It was going down, actually. Maybe I could share
okay.
again. I show you. I was running out of time, so I.
Okay, sorry.
Yeah. So could you see something? Do you see
Acknowledgement.
Oh, okay.
Acknowledgement.
So you see the acknowledgement. Okay, 1 second. Okay. So. 1 second. Okay. So you could see the thing there. Okay.
Yeah.
You notice that it was going down, and it was going down in the trend, and we were all very happy about that until we opened up everything. And then when I started opening up, you notice that it's increasing again. Actually, when I was predicting things at this point, it was going downhill. And then a few weeks from, I think 2 weeks, 3 weeks ago, it started going up again. And that's because of the the easing that we have done, the opening of the business. It's kind of interesting because the data is actually telling us the story of this. One of the puzzles that in the beginning when we did this, we didn't use the day itself, the Monday, Tuesday, and so on and so forth. And so we were getting wider intervals. And then I started noticing a certain pattern in the plots, this wiggly pattern. We thought maybe the day matters. Why should it? But the question is, why should it matter? If I am a COVID-19 patient, I don't have any control of when I'm going to die. Isn't it? I couldn't say, oh, let me die on Tuesday. Let me die. So technically, from a theoretical point of view, the distribution of days that people are dying should be uniform on the 7 days. So the question is, why is there a trend? And then it turns out that the trend is because of the reporting. These are reported daily deaths. So somebody might die on a Sunday, but it gets reported on a Monday. Somebody might die on a Tuesday, and then gets reported on a Thursday, something like that. So that's why the frailty, that gamma distributed random variable kind of incorporates the variability that is entering the picture, aside from the day effect. And so when you look at the prediction, you notice that it actually follows the thing there. Yeah, it is very, very interesting in that way. But it's going up. And now I'm very scared of extrapolating too far away because so many things could happen. And so if you extrapolate 1 month ahead of time, things could just blow up. And I don't think it's proper. Some people, the University of Washington people, in MIT people, they extrapolate too far ahead. And I think it's a very risky thing. Yeah, that's why I quoted Niels Bohr, that it is difficult to make predictions, especially about the future. So it's a risky business for statisticians to forecast too far away. Yeah, especially in this case that the daily deaths or the daily cases is very much affected by feedback loops. Whatever the government decides, it could have an impact on what will happen 1 month from now. So, and maybe because Trump had started wearing a mask, maybe it could help someday. Yeah, so I don't know. Yeah, but it's an interesting data set. It's a very crude way of modeling, but at least it gives us some answers somehow. Yeah, the details are in that archive paper. We took it as a problem of creating prediction regions for a general Poisson regression model, and then the over-dispersed, and then we just applied this in this COVID thing. So it's quite interesting. It was kind of a challenge, but the tools that we utilized are not very complicated because it's the delta method, the asymptotic normality, and so on, and that allowed us to do this. But it's an application, nice application to something that is happening. So I thought it's nice.
Okay, we have last question here, the number two of Gil Mendoza's question for Edsel.
Oh,
so,
he has part 2, okay? So what is part 2?
Is the concept of prediction region different from the common statistical idea of confidence region? If the same, why not call it as such? What can I deduce from your model? Yeah.
Yeah, confidence regions is when you're building a region for a parameter, like the mean or like the median, for instance. The prediction region, on the other hand, is you're building a region for a random variable. Okay, like what we're predicting is actually a random variable, so it's not fixed. Okay, so so that's why you call it a prediction region. But the principle underlying it is the same. We set up a pivotal quantity, just like what we do for confidence regions or confidence intervals, and then invert that to come up with a thing. But here you're predicting something that is random. So that's the difference. So because you're predicting something that is random, there's an additional variability that goes into the picture, and that's associated with the randomness. Just like in a simple or multiple linear regression, you also have the prediction region, which is wider as compared to the mean, the confidence region for the mean function. So remember in our basic books, the prediction region is a lot wider as compared to just the confidence region for the mean function. And that's the same thing, except here you have a Poisson distributed random variable. And then the question is, how do you do a prediction region for the cumulative one? Some people would use Richard's model. They actually do the prediction itself in the cumulative ones. What we did is to predict daily and then to accumulate. And we exploit the independence of the daily deaths. And then we use the Poissonness of the number of deaths daily. And then aggregate it. And I thought that was a better approach to do that. Yeah, but it remains the same. Yeah.
Final question: age adjustment in your model?
Mm-hmm.
Is there age adjustment?
Oh, we didn't, because we didn't have that data.
Yeah.
The data that, but you could, data that we have is just the daily cases, and then the daily deaths, and then the daily cases, and then the cumulative deaths. But you could actually do that. You could stratify with respect to the age. And then you could do actually the state by state too. You could also do that. Actually, we told Ben, one of the co-authors there, to look at the state one, because you couldn't aggregate. So I was more interested in the daily one, so in the whole US. And I also look at actually other countries like China, the Philippines. The Philippine data is a little bit suspicious to me, by the way. I'm not sure if we are getting a very reliable data from the Philippines. Because if you look at it, the patterns are simply not there. I don't know. So you're all in the Philippines. You have to. Okay. But European data, the European countries' data seems to be okay. But the Asian data were a little bit suspicious to me. But you could try to utilize these types of models, I think, to do that. It's kind of interesting. It's quite nice, yeah, to apply something on a real data set that is changing every day. It's a challenge.
Okay, so we have to thank Dr. Mariano and Dr. Pena for the very interesting talk. Now let's move on to the next speaker. Our next speaker finished PhD in statistics at University of Maryland, Baltimore County, where she worked on multiple testing controlling for false discovery rate with applications to genomic data. A paper she co-authored entitled Oncodomains, a protein domain-centric framework for analyzing rare variants in tumor samples, won PLOS Computational Biology Research Prize in 2018 for its public impact. Prior to that, Dr. Gauran already received third prize in the 2013 Jan Tinbergen Prize for Outstanding Young Statisticians from the International Statistical Institute. She finished BS and MS Statistics degree at the School of Statistics, proud advisor here, where she is now Associate Professor and Director for Research. Please welcome Dr. Iris Ivy Gauran, who will talk about local false discovery rate for sparse count data in the discovery of hotspots in protein domain. Dr. Gauran.
Good morning, everyone, and good evening to some. So I am Iris Ivy Gauran from the UP School of Statistics, and I will be presenting our work entitled Bayesian Local False Discovery Rate for Sparse Count Data with Application to the Discovery of Hotspots in Protein. This is a collaborative work with my PhD advisors at UMBC, Dr. Junyoung Park and Dr. Dohan Park, with our colleague Marisol Khan from the Department of Computational Biology and her students Ilya Ratsev and Tom Peterson. So in this talk, I will try my best to tie in together three related and that we did as it relates to hotspots. So the motivation of our study is in protein domain analysis as it is applied in cancer. So as we know, our fight against cancer is hindered by its very heterogeneous nature. Cancer arises when there are genetic mutations in the cell, which leads to abnormal growth and eventually to a tumor. However, the dilemma is that traditional methods for identifying somatic variants that drive cancer are gene-centric in that they only consider somatic variants within a particular gene and make no comparison to other similar genes in the same family that may play a similar role in cancer. So in our study, our initial work aims to coin and propose the term oncodomain hotspots, which is a new domain-centric method for identifying clusters of somatic mutations across entire gene families using protein domain models. So we know from the central dogma of molecular biology that DNA makes RNA and RNA makes proteins, and that the information is passed through that pathway. But that's no longer the case now in the presence of the field of epigenetics. So in our study, we were able to look into the overlap of the oncodomain hotspots with the active sites of a catalytic domain of protein kinase, also known as CD00180. So in figure A, we will see the active sites or the sites which are frequently mutated among different types of cancer. And in figure B, we will see the literature-based active site residues. And overall, in our results, we're able to show that there's an overlap between this. Another application that we have to protein domain data is by analyzing at least 5,800 patients from the Cancer Genome Atlas and the following patterns of protein domain hotspots on the calcium binding domain of epidermal growth factors, or CD00054, was observed. So as we can see in green, those are 3 residues that are known to bind to calcium. And in our study, we were also able to identify them as hotspots. In addition, we were able to identify 42 other residues, which are in blue, which did not bind to calcium, but tend to cluster around the binding pocket of calcium. And in this case, these positions were highly mutated for many patients. And in particular, one of our colleagues, Tom Peterson, discovered that known cancer variants tended to cluster at specific positions more than variants involved with unrelated diseases. So the main question now is, why did I start with the end in mind? So I started with a result or a set of results that we have for some of our work. And the question really is, in the process of understanding cancer, we wanted to look into the level of protein domains. So that further leads to the question that if we're not very familiar with the topic, so what are protein domains? So protein domains are unit of protein structure which evolve, function, and exist independently of the rest of the protein chain. As I mentioned in the previous slides, an example would be catalytic domains, or CD00180 and CD0054, and both of which are catalytic domains of protein kinases, and we're interested in them because they have been implicated in the development of various diseases, including different types of cancer. So let me shift gears a little bit and take on my statistician's hat. So let's look at what the data would look like in our perspective. So consider a given protein domain, and in a specific domain, there are big N positions. So the data will look like a vector A sub n, where the ith value is the number of mutations in the ith position. So this is what CD00 will look like in terms of its bar plot. So we can look at the bar plot because it's interesting to highlight certain features of the data set. So the first feature that we can see is that there are a lot of zeros. So that would mean that there are a lot of positions in the domain with 0 mutations, which is kind of good for the patients involved. Another thing is, it is not surprising to see a lot of ties because we're dealing with count data. So we can see several positions with 0 mutation count, several positions with 1 mutation count, and so on. Another thing that we can observe is that there is a possible over-dispersion as it relates to Dr. Pena's discussion earlier. There is a possibility of over-dispersion that this data might display. And lastly, in terms of providing a direct-to-the-point assumption on the model that is probably involved in this study, it is a zero-inflated discrete distribution. So the main overarching objective of the study is to test which among the positions are background mutations, which among the mutation within the positions are background mutations, and which among these are related to the disease, or what we refer to as functional disease mutations, while controlling a given level of type 1 error, such as the false discovery rate. So the main dilemma in testing this set of hypotheses is, how do we specify what F0 is? So we know AI is the number of mutations in the ith position, but what does the null distribution look like? So to be able to proceed with the testing procedure, we need to make certain assumptions on the null distribution F sub 0. So here, we were using the idea of empirical null estimation, that is, F0 is estimated based on the data, rather than some predetermined distribution, such as the standard normal distribution. In addition, we will use Efron's zero assumption, wherein most of observations concentrated around the center are considered to be null observations, but those towards the tails will be considered or will tend to be non-null observations. So the main dilemma for us is to extend this in the discrete case. So in our case, our main assumption is that the mutation count, which belongs to the set 0 to capital C inclusive, for some unknown integer C, is generated from the null distribution. So to visualize this, our one-stage procedure proceeds by specifying the mutation counts from 0 to capital K, where capital K is the maximum number of mutations in a given protein domain. And then our goal is to estimate C by C hat using the EM algorithm for truncated data by McLachlan and Jones. So once we are able to identify C hat, every mutation count from 0 to C hat is considered to be background mutation, and we do not reject the null hypothesis. Otherwise, if the mutation count is from C plus 1 to capital K, we will test using the local FTR. So an extension of this procedure that we proposed is the two-stage procedure, wherein after identifying the value of C hat using the estimation procedure, by the way, all the estimation procedures are available in our paper, and I will gladly talk to anyone who will have questions about it. In the interest of time, I decided to just summarize the proposed methodology in this presentation. So after identifying C hat, our goal now is to identify D hat. So analogous again to the work that Dr. Pena is discussing earlier, we are looking into the tail probabilities of the zero-inflated generalized Poisson distribution, which is our null distribution for the mutation counts. And we know that from literature that this generalized Poisson distribution with the zero inflation parameter accounts for the over-dispersion in the count data. So the tail probabilities used in calculating D is actually based on the large sample theory. So it requires the sample size or the number of positions in a domain big N to be large. Now, what we do is, similarly, we do not reject the null hypothesis if it's a number between 0 to C hat, and we automatically reject if it's from D hat to K. For values between C plus 1 to D hat, we test it using. So with this study, the question is, why did we decide to go Bayesian? So why go the Bayesian route, apart from the cliche that you do the frequentist route and then eventually you do the Bayesian route? We really have a very valid and solid reason for proceeding this route because there are two types of protein domains. So there are domains which have large number of positions ranging from the hundreds to thousands, and there are positions with very few there are domains with very few positions, which are even lower than 100. So an example of this is the helix loop helix domain, which is a catalytic domain again. HLH domain is very helpful for the processes of neurogenesis, sex determination, and gut development. So understanding the behavior of this domain, no matter how difficult it is to study, is very important for us. So if we look at the plot, it kind of looks the same as the previous bar plots that I've shown earlier. The main difference being the number of counts here is, the total number of positions in this domain is 93 only. And as we can see, it's still zero inflated, but it displays not only a small number of positions, but sparsity as well. So we wanted to use the smoothing property of Bayesian approaches in order to address this problem. As a response, if we just use the large sample approximation assumptions that will not hold for sure, C is underestimated in all of our numerical scenarios prior to running the full Bayesian scenarios, and pi 0, which is the proportion of the null observations used for the calculation of the local false discovery rate, is underestimated. In essence, this will consequently lead to inflated false discovery rate. So with that said, we proceeded with some histograms. So as you can see here, this is the simulated version of the data that I have shown here. And we tried to simulate it using the null distribution, which is ZIGP, and shifted geometric as our alternative or non-null distribution. So we are showing 3 cases for this one. So the first one, when C equals 5, all gray values represent true null observations or true null mutation counts, whereas the black values represent non-null counts. So that means all black values should be rejected for us to have a good power. And gray values should not be rejected so that we won't commit false positive error. So in this case, the significant values will just start from 6 up to the maximum possible. Whereas in the second case, we start with 2 onwards. So we just reduce the possible values of C. Instead of it from 6 onwards, we allow smaller values of C to be even considered as significant functional disease mutations. And the most important test that we did for the series of numerical studies that we employed in this paper is that what if we are testing the key assumption on the existence of C. And what if there is no C in reality? So that means even some of the positions with 0 mutation count can be attributed as functional disease mutation. So that kind of does not make sense for me without that much biology background, but we are just testing it to check the robustness of our assumptions. So here is the table of a sample of results, some results that we have comparing our proposed non-parametric method versus the existing empirical based method that we did when we assumed that the number of observations is large. So as we can see here, the true value of C is 5, and the procedures that we are comparing assumes Dirichlet prior, and both of them are near continuous uniform priors. And then we compare that with our 2-stage, 1-stage procedure, a very popular stories procedure in the multiple testing realm as well. So we assume a 0 inflated model for our null distribution. It could either be ZIGP or the specific case when we don't account for over-dispersion, and that's the 0 inflated Poisson distribution. R represents the number of rejected positions, and FDR represents the false discovery rate, while true positive rate corresponds to the empirical power. So in this case, we can see that for all values, under the assumption of ZIP without accounting for over-dispersion will yield to inflated false discovery rates. Whereas when we assume that there is over-dispersion in the model and we account and estimate for that, then the value of the FDR is controlled given that our true nominal value is 0.05. So this is the actual result with the helix loop helix domain that I have shown earlier. So this is for the real data result. As we can see, the empirical Bayes method yielded 7 rejections. Our proposed non-parametric method, together with other methods such as semi-parametric and parametric Poisson and parametric generalized Poisson, yielded NP yielded 1 rejection. And we can see the orange vertical line to be the cut-off point for the EB model. This is under the assumption that everything after this cut-off point are rejected. So I'm not 100% sure it's very clear, but we can see 3 mutation counts here, 2, 1, and 1, and that will add up to 7. Whereas for the non-parametric method, only 1 value is rejected. So that is true for HLH. And then this is for sushi repeats, wherein in this case, we can see an even clearer distinction among all the methods. So in this case, we can see that the orange, which is the earliest cutoff, corresponds to the empirical Bayes. Then the red one, which is the next cutoff, is for the non-parametric method. And then the most conservative in this case is our semi-parametric method. For curiosity purposes, the parametric and non-parametric assumptions vary in terms on how the overall mixture distribution F, or the alternative distribution F1, is specified in terms of their priors. And another application is another epidermal growth factor domain. And in this case, we can see that there is the value for empirical Bayes and non-parametric result method coincides. That is true regardless of the null distribution. So there are some cases that the non-parametric method in a way converges to the result of the empirical Bayes. So all of this are part of our body of work. And the most recent result that we were able to look into is in another catalytic domain, CD00083. And in this data set, we were able to find position 15 of the HLH domain, which is highlighted in red. And this was identified by both methods, empirical Bayes and non-parametric method, as a hotspot, whereas the other blue parts are identified by the empirical Bayes method as hotspot as well. So the red part is actually a proven DNA binding position, which verifies the results that we have in this study. So looking into everything that we've done in this body of work relating to proteins and coming back to the Philippines after my PhD graduation, I am now working in terms of proteins as it relates to lung cancer in coordination with the Lung Center of the Philippines. And we're also studying it in the protein level. So the applications of this one, while slightly, the schedule is moved slightly because of the COVID pandemic, is still being applied to the Philippine scenario and in a specific cancer, and that is lung cancer, as funded by DOST. So with that said, these are my references. And I would like to thank Ma'am Gisela and Sir Erniel for organizing this talk. And special shout out to Sir Mario Santo Domingo and Ma'am Leia Tolosa for always inviting me into the PAASE events, especially when there's tons of food during the time that I'm still a graduate student at UMBC. Thank you po.
Okay, thank you very much, Iris. Please reserve your questions for later, or better yet, you can type it at the Q&A box. We will read it later on. So let's now proceed to the next speaker. Our next speaker also started from the Statistical Center, the predecessor of the School of Statistics, where he obtained his BS and MS Statistics degrees. He also held a teaching position at the School of Statistics before he proceeded to Lund University to earn his PhD in statistics. He was and is always in marketing science. We worked together in some projects a long time ago. Now he is still in marketing science, but is looking at how data science can complement. At present, he is with the Department of Statistics of Lund University, and also connected with GFK, perfect formula of the necessary collaboration between the academe and the industry for data science. Doing analytics for marketing science problems, his talk today on option framing is one such example. Please welcome Dr. Antonio Maranon. Tony? Tony?
You're muted, Tony.
So,
can you see my slides?
Yeah. Okay.
All right. Okay, after 3 fantastic papers, I think this one is a breather for many. There will be no error terms here or white noise or difficult things, but instead, when Erniel called me up for some paper, I thought that I would share a current project, which was done through the marketing science group. So, good morning, everyone. My name is Tony Maranon, and together with Peter Gustafsson, we are going to talk about evaluation of option framing in car inspection services. So I hope you will 100% understand everything what we say here. In Sweden, vehicular inspection is mandatory, as in many other countries, but in the recent years, this has been regulated and opened up for private competition. One of the leading companies which offer vehicular inspection services approached us just recently for assistance regarding the choice of framing in the point of sales presentation of their service offer for potential customers. The service package is straightforward, composed of 4 components. The first component is required. It's the basic mandatory inspection as specified by law and priced at 395 crowns. And then we have 3 additional options. Additional control of electronics, 100 crowns. Additional fluid control, 50 crowns. Additional tire control, also 50 crowns. The framing in question is either additive or subtractive option framing. In additive framing, the customer is initially presented with the basic mandatory inspection component or the base model. Thereafter, the customer is asked if he or she wishes to add any of the 3 additional options. In subtractive framing, it's the other way around. The customer is initially presented with a full package or full model, that is the basic package plus all of the 3 options. And now the task for the customer is to deselect or remove any of the 3 additional extra options. So the primary aim of the study, which is a consultancy project, is to compare and evaluate the decision scenarios of the 2 frames, something along the line of Markov chain modeling. But from the company's perspective, the interest lies on which framing gives better financial benefit for the company, which framing gives larger financial service package. Now, the study takes its inspiration from Tversky and Kahneman anchor theory, which states that the consumers tend to hold on to the initial point, making small adjustments to the number of options around the anchor points. So if we apply this to our study, for additive framing, the consumers tend to add fewer options to the base model. And for subtractive framing, the consumers tend to refrain from deselecting options from the full model. So in this case, we should expect that consumers tend to select more options when following subtractive framing. And this gave rise to possible descriptions of rational customer behavior, wherein those undergoing additive framing experience risk of losing money, and those undergoing subtractive framing encounter risk of losing service quality. The framework of the study includes the risk components in relating framing of service options to the final choice or configuration. We have also included uncertainty about prices in the study. Some customers were not informed of the prices of the additional options or extra services, and we would like to see the effect on the final configurations. And Peter?
Thank you, Tony. The design of the study, the experiments, due to the client's direct need and tight schedule in this very new market situation, we decided to focus on the number of chosen options, not which ones, and model the customer's decisions as a Markov chain at different stages. Note that the number of options represents different states in the Markov chain, and the transition probabilities between states represent the actual measurements of a risk aversion or risk behavior of the consumers. So we have a Markov chain model of option frame structures. We have 3 stages. 0, the service concept is presented and the respondent evaluates whether or not the concept is to be considered. Here we only have 1 state, number 0, no selection. At stage 1, given that the respondent is positive towards the service concept, the initial package is presented and the respondent then evaluates the options following the framing structure. At stage 1, we only have 2 states, state 1, base model, or state 4, full model, depending on which kind of framing structure we have access to the respondent. At stage 2, the final stage, should the respondent wish to modify the initial package, a final configuration of a service package is done. Here we have 4 possible states, 1, 2, 3, and 4, depending on the customer's choice. So we have 4 possible experiments. 1, additive framing, not showing prices for the options. 2, additive framing showing prices for the options. 3, subtractive framing, not showing prices for the options. And experiment 4, subtractive framing showing prices for the options. Here's the results of the 4 experiments. Here we present the actual measurements of the transition probabilities at different stages and for the different states. If we, for example, look at additive framing without prices for the options, we can see that most of respondents try to hold on to the initial model, 0.7%, which is an indication for anchor theory. And if we look at the 3 other experiments, we still have this tendency to hold on to the initial state, independent of the framing structure. A nice confirmation of anchor theory, actually.
Okay, there are 6 hypotheses that we would like to discuss with you today. And hypothesis 1 is actually what the client or the company is most interested. Didn't care much about hypothesis 2 to 6. For the client, they really want to know what the expected values are. So hypothesis 1 is we claim that the expected values of the number of features in the final configuration is greater in subtractive than additive framing. And to test this hypothesis, we simply compute for the truncated expected values of the number of features in the final configurations. And as expected, both subtractive frames have higher truncated means than any of the additive frames, almost double. The differences are statistically significant.
So, during hypothesis 3, the type of option framing affects the form of the final state distribution for the initial models. For this hypothesis, we create the distribution of a distance from the initial model. That means, more or less, if we have a shape and form of the distribution functions here, we can see at a distance of 0 represents that we still are at the initial model. A distance of 1 represents that for additive framing, the consumer has added 1 more options to the base model. And for subtractive framing, that means that the consumer has removed 1 of the options, and vice versa for 2 and 3. What we can see here is that for additive framing, the bars with blue and turquoise, we have a monotonically decreasing function. The larger the distance is from the initial point, the smaller the probability that the consumer will choose that many options. And for subtractive framing, the yellow and red bar, we have a U-shaped function indicating that we have a switching point. For very long distance from initial model, the consumers tend to switch behavior in favor for low prices. And we can also say that the difference between these two distribution functions are statistically significant between additive and subtractive framing, but not within the respectively frames. So, hypothesis 3. This is about anchor theory, actually. The non-transition probabilities for the initial models based on full tend to be larger than other movements. According to the anchor theory, the consumers tend to hold on to the initial model. This tendency can be evaluated by comparing the transition probabilities in a Markov chain setting for this study, showing that, for example, for additive framing, the non-transition probability as state 1, nu 1, 1, is always larger than all other transition probabilities. And for subtractive framing, the non-transition probabilities at state 4, the initial point, is always larger than all other transitions. For both hypotheses, the test of difference between the non-transition probability at the initial point and the other movements from the initial model to another state are all significant. Another confirmation of anchor theory.
Okay, for hypothesis 4, we have the knowledge of the prices of the options affects the transition probabilities in both additive and subtractive framing. In this case, we have 2 groups with prices and without prices. So for additive framing, we compare the aggregates of the transitions 1, 2, 1, 3, and 1, 4 for the groups with prices and without prices. And for subtractive framing, we compare the aggregates of the transitions 4, 2, 4, 3, and 4, 1, again for the groups with prices and without prices. And the results are as follows. For additive framing, the aggregate transitions for with prices is higher than without prices. Then you can see they're 0.411 with respect to 0.298. This indicates a tendency to choose more options when the customers know the prices. They move on to a higher level once they are comfortable with the prices. Now, for subtractive framing, the aggregate transitions for with prices group is lower than without prices. And how do we interpret this? This indicates a tendency to hold on to or maintain more options when the customers know the prices. So the results confirm earlier price sensitivity studies. Prices deemed acceptable is indicative of positive transitions to more options in the final configuration of the option framing. And when we looked into hypothesis 5, this is again, we're trying to prove Kahneman's anchor theory here. But for hypothesis 5, we looked into the non-transition probability for the base model in additive framing. If it is larger, we expect it to be larger than the non-transition probability for the full model in subtractive framing. If this is true, then this implies that anchoring is stronger in additive framing. And the real question here, which non-transition probability is strongest? Is it nu 1-1 in additive framing or nu 4-4 in subtractive framing? And in both cases, without option prices and with option prices, we can see here that nu 1-1 is greater than nu 4-4 in support of the hypothesis that anchoring is more pronounced in additive framing. But there is slightly a difference in the test results, because for the group without option prices, the absolute difference is significant. But when the option prices are known or revealed, the absolute difference of non-transition probabilities is not significant. So no matter what framing process is used, the suitability of the prices of the options can favorably affect the final service package. The framing comparison for the with option prices case can be used to verify price sensitivity results. And finally, our hypothesis 6.
Hypothesis 6 is more about the balance between losing money or the risk of losing quality. So the risk of having to pay higher prices for services is more intense than the risk of lowering service quality. To verify this last hypothesis, we use the distribution of the distances from the initial model already evaluated. Earlier, it has been shown that the final state distribution for distances from initial model are significantly different for additive and subtractive framing. Following the formative computation of truncated means, the estimated expected distances for the corresponding initial model are as follows. We can see here that if the expected distances is 0, that means all of the respondents in the experiment keep on to the initial point. And if the expected distances have a value 3, that means that the respondent either remove all of the 3 options for subtractive framing or add all the options for those who are accessed to the additive framing experiments. Now, the results. Additive framing without prices for additional options, the expected distance here is 0.4. Very small distance from initial point. Consumers are very reluctant to move to leave the initial point. If we include the information of the prices, the expected distances is a little bit larger, 0.6. But for subtractive framing, both with and without prices, the expected distances is a little bit larger, 1.2, respectively around 1, indicating that it is more reluctant for the consumers to keep on to low prices and high quality. So here we have implications for the theory and practice in future directions. When we started this project, it was only possible due to the market situation to measure what we call the initial model. All the consumers must start at stage 1, at stage 0, at state 0. And then we can only have this very simple Markov chain structure. But now we can expand this initial model to what we call the entry point model, which includes all possible states and all possible transition probabilities.
All right, some concluding remarks. Based on the 4 experiment groups, we see that subtractive framing is a clear winner. So that means that if you have the option of presenting your products or your services, the way wherein you will get more financial benefits is to do it in the subtractive way. Present the entire model and then let the customers remove instead of building up the final package. We also discussed earlier the distributions of the distances from initial model, and additive framing has a monotonically decreasing function, subtractive framing U-shaped function, and the differences in the shape of this behavior of these framings can lead to the differences in expected distance from initial model, which shows that the risk of paying higher prices is more intense than the risk of lowering service quality. We also we have seen that the anchor theory is very much pronounced on the in the additive framing situation. Very strong impact of the initial model for the additive framing as opposed to the subtractive framing. But when we showed the prices for the options, it had a significant effect on lowering risk aversion, which is very important that price sensitivity studies should be done in parallel to determine the acceptability of the prices of the options. For future studies, other constraints will be analyzed in the same way as price subgroups used in this study. It would be interesting to explore further applications of market shape models in other scenarios or types of option framing. Entry point model, which Peter discussed earlier, using actual options as states in sequential studies, which we're going to do in another consultancy project for solar panels for households, and a more intricate state space modeling, incorporating explanatory variables such as age, brand of car, previous experiences with service inspections. What I can say is that it has been a delight in applying Kahneman's anchor theory in this project, in this very short project, in option framing. So I hope you gained a little marketing science insight from our short presentation. Thank you very much.
Thank you very much, Tony. So again, please reserve your questions, or better yet, type it in the Q&A box for the speakers to reply on them later. But let's now move on to our final speaker. She completed BS and MS Statistics degrees from the Statistical Center, my batchmate actually, where she also held a teaching position. She finished PhD Statistics at the School of Statistics, University of Minnesota. She also taught at Bowling Green State University before joining the Department of Statistics at Harvard T.H. Chan School of Public Health as a research scientist. Her research focused on communicable diseases. She will talk about the risk-benefit outcomes for studies in tuberculosis, treatment, and prevention. Please welcome Dr. Grace Montepiedra. Grace, you are still muted.
Can everyone hear me?
Yes.
And can you see my screen?
Okay. You can show it now, Grace.
Okay, can you see my screen?
Yeah.
Okay, thanks, Arniel, and good morning to everyone, and good evening to those of you who are on the East Coast. Great to see old teachers, old colleagues. Edsel, I noticed that you are chess is still a big part of your life. So anyway, we're segueing now to the field of clinical trials, which is what I've been involved with for the past maybe 15 years of my career. I've been doing a lot of clinical trials work in the field of HIV, and as well as in the field of tuberculosis, which is a very common comorbidity of populations with the HIV disease. So I'll be presenting really I'm not going to show any formulas or anything. The first part of my presentation is really going to be sort of a motivation behind the approach, a very simple motivation behind the approach specific to tuberculosis, and then 3 projects that sort of are using this approach, a couple of applied ones, and then one more methodological. So tuberculosis, I think many folks are aware that it's the #1 cause of death globally among infectious diseases. Philippines actually ranked #3 in prevalence rate as of last year, according to WHO, with approximately about 1 million with active TB. And the most common type of TB is the drug susceptible type. So there's it's a type of TB that's not resistant to any of the drugs. It needs 6 months to treat drug susceptible TB. We need 6 months of 4 types of drugs: isoniazid, rifampicin, pyrazinamide, ethambutol, also known as HRZE. And then there's a more and more commonly appearing now, there's sort of starting to be an epidemic of what's now called multi-drug resistant TB starting in the 1990s. And what it is it's basically resistance to the basic background drugs for drug susceptible TB, which is isoniazid and rifampicin. And it takes longer to treat it, 9 to 12 months of at least 5 drugs. And worse than that, it contains an injectable, daily injectable regimen, which can be very painful and has lots of toxicities. It's also called the Bangladesh regimen. And then the most dangerous type of TB is extremely drug-resistant TB, which is resistance to many of the second-line drugs for treating MDR TB. So, you know, just sort of a motivation. Suppose that a person has been diagnosed with MDR TB. Then suppose that in a clinical trial, there are 2 treatment options that are being studied. The one is the standard Bangladesh regimen, which is, as I mentioned earlier, it's a long, almost a year worth of 5 drugs containing an injectable, versus an experimental regimen B, which is a shorter regimen, which is 6 months, and will not be using an injectable. So given these 2 options, which one should you give? So what are the main factors that normally we test to sort of help us decide which one of the regimens is the better regimen? Well, the main factors are, of course, efficacy. You want to make sure that the regimen has a clinical benefit, that it will treat the disease. And of course, safety. You want to make sure that, you know, you want to minimize the risk, the toxicities of the drugs to the patient. There are also other factors that might play a role. There's the issue of tolerability. You know, will the patient be able to take the regimen for a long period of time without much issues? There's quality of life. Is it going to hinder daily activities of living? So there are these several factors, but the main factors are the ones that are typically being tested in clinical trial. And the standard approach is to have 2 sets of hypotheses. Usually there's a primary objective, which is usually the efficacy objective, which is usually a superiority, you know, which one's better, or a non-inferiority objective. So in this particular case, for example, would regimen B be non-inferior to regimen A? And then there's also going to be a safety objective, which is to compare the superiority of one regimen over the other. And sometimes safety is relegated to a secondary objective. So in the conventional approach, what we do is what we call analysis of outcomes. What that means is that you first look at one outcome, in this case, efficacy, and then you compare the two regimens. And then next you compare safety, and then you compare the two regimens with respect to that outcome. So suppose that we have two regimens, A and B. I think everybody's pretty familiar with this type of approach. And suppose that we have 3 patients assigned to each regimen. And suppose that regimen A had 74% success rate, regimen B had 65% who were cured using regimen B. The relative risk is 1.31, 95% CI, which is greater than 1. And so it shows that regimen A has a better success rate, treatment success rate than regimen B. However, when you look at the safety, when you compare the two regimens, turns out regimen A has more toxicities with 50% serious adverse event rate compared to regimen B with 40%. So the comparisons are in either direction depending on which outcome you're looking at, whether it's efficacy or safety. So the question is, does the clinical benefit derived from choosing regimen A outweigh the higher risk of toxicities from using that same regimen? So that's the issue with doing separate analysis of outcomes. When it comes down to actually making a choice, it's really hard to look at the risks versus the benefits in a quantifiable way. So the one approach to sort of help, with making those kinds of decisions, the risk-benefit decision, is to think of the, instead of analyzing outcomes, the approach would be to analyze patients. You look at a patient and look at the overall, the totality of experience of that patient. So in this particular case, we look at the totality of experience of a patient with respect to both efficacy and safety. So if it's efficacy is binary and then toxicity or safety is binary outcome, then you have basically 4 possible outcomes. And among the 300 participants who were subjected to regimen A, they would belong to one of the 4 different possible combinations of the 4 possible outcomes. So the table at the top shows you the different distributions of the 4 possible outcomes for regimen A, and then for regimen B, likewise. Now we can show those 2 tables. We can combine them into this table that you're seeing in this slide. But the important thing here is that those 4 possible outcomes could actually be ranked according to what we call desirability of outcome, where you prioritize these 4 different potential outcomes in terms of the patient experience. So if for example, between efficacy and safety, efficacy of a higher priority and safety of is the second priority, then if you look at the possible combinations, the 4 possible combinations, it makes sense that the most desirable outcome is treatment success with no toxicity. And then the least desirable outcome would be treatment failure, drug doesn't work for clinical benefit, and a toxicity occurs in the patient. So it's a very simple, just sort of showing a very simple scenario, very simple table. And the comparison, the distribution of the 4 possible outcomes for regimen A is shown in the second column, and for regimen B, likewise, in the third column. And there are, of course, many different issues that we would encounter with clinical trials, loss to follow-up, competing risks, and all that stuff. But for the sake of simplicity, just to drive the issue here, we would just use a Wilcoxon rank sum test, or any test that you could use for ranked outcomes. And it turns out it becomes now, instead of, for example, a non-inferiority comparison of efficacy and a superiority comparison with respect to safety, this will turn out to be just one superiority comparison of this, what we call risk-benefit outcome. This 4 category outcome. And it turns out with the superiority comparison, it turns out the Wilcoxon p-value turns out to be significant. One way to estimate sort of the effect, sort of the treatment effect of regimen A versus regimen B is to use, or is to estimate the probability that a patient, that the randomly chosen patient taking regimen A will have a better outcome than a randomly chosen patient taking regimen B. So that's one way to sort of estimate sort of the overall treatment effect with respect to risk-benefit outcome. Let's say in this case, we get 55.4%. With the 95% CI, that's above 50%, which basically tells us that regimen A is actually the better outcome in this, the better regimen in this case with respect to this risk-benefit outcome. So it's a sort of a simple example of how this risk-benefit approach, using this risk-benefit outcome, comes into play. So this was sort of popularized in the clinical, in the clinical literature by Scott Evans, who also belonged to our group at the School of Public Health. Was called the desirability of outcome ranking. It's getting to be a more and more sort of a popular type of outcome, or we call it DOOR outcome, and it's used in can be used. He generalized basically what has already been proposed in the past, as I'll show you in the next slide. Myself and some colleagues of mine at the School of Public Health sort of discussed the applications of this ranked outcome in the field of tuberculosis, treatment of tuberculosis. And as I mentioned earlier, there are, this type of outcome has been proposed in the past as a rule-based ranking scheme, first by Christy Chuang-Stein and her colleagues in stat medicine back in the 1990s, Dean Fallman from the NIH also back in the 1990s. So the sort of the rule-based method, ranking method that I mentioned earlier, is kind of sort of the similar approach as the Chuang-Stein and Fallman approach. But there are different other approaches, ways to prioritize the outcomes. Another approach is by doing a survey. You give them all these different categories of patient outcomes, and the sort of a Delphi panel, what's called the Delphi panel, would be sort of ranking them. So a Delphi method is one approach, and then another approach that is actually quite interesting, much easier for participants to do, especially when you have a larger number of categories. It's what is called discrete choice experiments, very popular in marketing research. For those of you who are in that field, probably might have heard of it. And yeah, we're also looking into that as well. And now I'm going to be showing you some three projects that I've worked on with some colleagues of mine. One is an application to a TB prevention study. It's called Brief TB, and it was a clinical trial conducted by some of my colleagues at our center. It's a TB prevention trial that's comparing a short regimen of isoniazid and this other drug called rifapentine as an experimental regimen, compared to the standard of care of giving 9 months of isoniazid for prevention of TB. So what's very common in the study of new regimens in TB prevention and TB disease treatment is shortening of regimens. Particularly in TB prevention, since patients are normally relatively healthier, they don't really like to take 9 months of INH. It's too long, and there's problems of adherence And you don't want, I mean, safety is a very big concern because this is a relatively healthy population. So in this risk TB study, there were 3,000 HIV-infected adults and adolescents with TB infection who were randomized to the shorter regimen of 1 HP versus the standard of care of nine months of isoniazid. This was published at the New England Journal of Medicine just last year, and it was shown that 1 HP had non-inferior efficacy to the longer regimen of 9H. So it is a non-inferiority trial comparing the efficacy with similar TB incidence rates found between the two arms. Now there's a secondary safety comparison between the two, but the main results really like focusing on the efficacy. However, being also concerned with safety in a TB prevention study, we have decided to apply the risk-benefit outcome to this particular data by first asking a Delphi panel, what we call a Delphi panel of several stakeholders. These are clinicians, TB researchers, knowledgeable in the area of TB prevention. And they identified basically potential categories of the risk-benefit outcome. So in this particular case, there were 9 categories that they were asked to rank. And, you know, for the efficacy, there's TB or no TB. And then for safety, severity of toxicity is actually very important. So you could have a patient could either have a grade 2, a grade 3, a grade 4 AE, or the patient could die, right? So a patient in the study could either have no TB and did not have grade 2 adverse event, which is the best outcome, the most desirable outcome. So the patient was rank 1, and then the worst is if the patient died, which is number 9. And it was just a simple comparison of these ranks of patients. Each patient is assigned a rank, did a flow taxon rank sum test, and turned out that the 1 HP is superior to the longer regimen with respect to the Wilcoxon rank, with respect to the risk-benefit outcome. So it sort of really, it supports the non-inferiority sort of conclusion that was reported in the main paper. Another application of risk-benefit outcome that we've done is to look at another TB prevention trial on pregnant women. This is the TB Price trial that's also performed in our group, and I was the statistician in that study. And the basic objective is to compare. This is another non-inferiority trial, but of safety. In pregnant population, safety is always an important consideration. Efficacy is normally already assumed to be true, extrapolated from the adult studies to pregnant women. So to compare the maternal safety of initiating 6 months of TB prevention during pregnancy versus deferring to postpartum after the woman delivers. The concern there is the safety during pregnancy. So in this particular case, there were 956 HIV-infected pregnant women who were randomized to one of the 2 arms. And the study results, which was again published last year as well, was that it was found that we were able to show that initiating INH at pregnancy for prevention of TB is non-inferior, or which so-called just as safe as deferring it to after the woman delivers. There are, you know, the main comparison here is safety, maternal safety, but there are so many other considerations. There's, of course, the efficacy, which is TB incidence rate, which was found to be similar between 2 arms, the maternal TB, but we also wanted to look at infant TB. So the maternal child health aspect of it, that TB prevention could also be beneficial for the children. And so we found that infant TB rates are very similar between the two arms. However, there was more maternal hepatotoxicity in the deferred arm. It turned out not to be significant, but we found more adverse pregnancy outcomes in the immediate arm, which is found to be significant. These are secondary comparisons. Adverse pregnancy outcomes are things like stillbirth, premature delivery, congenital anomalies, low birth weight. So given all these considerations in the mother and the infant, it begs the question, from the whole risk-benefit point of view, overall, when looking at all these different outcomes, primary and key secondary, was initiating 6 months of isoniazid just as worse than deferring it to delivery, so post-delivery. So I'm not going to give the full details, but basically what we did here was we had a more involved process of developing the composite outcome. What we basically did was we developed a maternal-infant composite outcome, which examined the safety and efficacy in both the mothers and the infants simultaneously. We used a focus group of 6 experts in TB research, and then we followed it with a 2-stage Delphi survey of 26 stakeholders, and we came up with this sort of a composite outcome, wherein the Delphi survey panel prioritized an outcome that consisted of mother-infant pair categories, showing whether if the mom had TB, the infant had TB, that's one category, etc. And then we compared the immediate versus the deferred INH, the TB preventive therapy in the data set with respect to the composite outcome. The bottom line is we did find that between 2 arms, there was no significant difference, but we did find an interaction effect between the study arm and the ARB regimen with respect to this risk-benefit outcome. The manuscript is currently in review, and this was presented last year at the Union World Conference on Lung Health. And then finally, more of now segueing to a more methodological approach. We've also looked at using the risk-benefit outcome in designing and analyzing non-inferiority trials. Basically, non-inferiority trials are really probably the most commonly used type of design in the evaluation of TB regimens. And one of the major issues, and it's a very big area of debate, there's actually a couple of papers in clinical journals at PLSO Medicine that really discuss this issue, which is the determination of the non-inferiority margin. For example, in drug-susceptible TB, wherein the main hypothesis is the non-inferiority with respect to efficacy of new TB regimens for treatment of drug-susceptible TB, they basically were using like 6% as a non-inferiority margin. And the rationale behind that has been under debate. But our contention is that the non-inferiority margin should really be providing, quantifying the trade-off between the benefit and the risk. You know, the trade-off of allowing a non-inferiority margin on the efficacy should be due to perceived benefits of the regimen, whether it's because of safety, whether it's because of tolerability, whether it's because of quality of life. The non-inferiority margin should reflect in a quantifiable way the perceived benefit of an experimental regimen that allows it to have sort of lower efficacy, you know, which is what we usually do in non-inferiority trials, is we allow a non-inferiority margin, which is sort of a small loss in efficacy. And so this is my last slide. some colleagues of mine at the center were able to have a unified we showed some equivalence between comparing the risk-benefit outcome with a non-inferiority trial, and we were able to quantify the risk-benefit trade-off using the risk-benefit outcome in comparing the two different arms. And we call it, we now introduce the concept of what we call a maximum allowable decrease in efficacy, or what we call MADE. And we propose to use that quantity to inform the non-inferiority margin in the non-inferiority trial. So this is we are planning to use it for many of our new non-inferiority trials that we're going to be doing in our group. It has been reviewed at the Statistics and Medicine, and hopefully it will be published very soon, and love to share with everyone once it's out there. And I think I'll end at this point.
Thank you very much, Grace. Okay, we have time for a few questions. Okay, so there's a question here for Dr. Gauran from Gerard Umpad. My background is in tropical medicine, and I'm wondering if the method you presented can also be extended to infectious diseases instead of studying genetic sequences that renders people susceptible to infectious diseases. One can scan and analyze protein domains instead. I am also wondering if the 3D structure of these protein domains may affect the analysis, that is mirror images of a target protein domain present in a single CD factor. Hi.
Thank you, Paul, for the question. So I'm not 100% sure about my answer regarding the protein structure. So I will just answer the first part of the question regarding the applicability of the method to infectious diseases. I think the short answer is yes, but it's a conditional yes, because we know that for infectious diseases, we have to accommodate a lot of confounder effects. So I'm guessing, which is part of the future directions of the work we've done, is to incorporate covariates and other available information. In the Bayesian perspective, we can accommodate them in the prior information, but in empirical base, we can consider them as covariates in some sense. So I think that would be very much a good extension. So siguro po a quick perspective regarding what I know so far about infectious diseases, which is COVID. So the project that we're working with under the Philippine Genome Center right now is to sequence viral samples of people who are positive with COVID. So the idea is to perform a metagenomics analysis for that. But so far, up to the level of protein domains, I don't know what the structure of the data set will look like yet, because the project has just started under the OST-PCHRD, but it hasn't reached the analysis stage yet. So we're still in the process of sequencing, and we don't know the available data to us so far. But one of the questions which I think is related to the question being asked is there local mutation happening in the Philippines? So are the mutations spreading, are the positive cases in the Philippines, the samples, do they contain specific mutations which is geographically constrained in a sense? So I think yun po yung perspective ko so far regarding the problem.
Okay, so any other question from the participants or from the panel? Yes, from Sulaiman.
I have asked a question to Grace. Just to clarify two questions. When those treatments, they just include different drugs, there is nothing additional food controlled, or are they the same? They have the same food also. The second question is, how does the vaccination of tuberculosis play a role? What is the efficacy of that if you compare it with these treatments? I know that's not, it may not be a major topic, but if you can say a few words on that, I'll be very happy.
Yeah, hi, thanks, Sulaiman, for your question. I think the first question was with regards to how so in treatment of TB, our standard of care, the control group, is typically for the drug susceptible for drug susceptible TB. The control group is the standard of care. So we do have standard of cares for drug susceptible TB. We do have standard of care for that, which is the 6 months of HRZE, isoniazid, rifampicin, pyrazinamide, and ethambutol. And then for TB prevention, we also have a standard of care, which is the 9 months of INH for adults. And the question about control is a really, really very important question because of the problem of biocreep, right? We're looking at more and more new experimental regimens and comparing it with this old standard of care. And once you have been able to show non-inferiority of a new regimen, then which one would you be using as your control group once you have shown that? So one is to be really careful about choosing a control group in the next experiment. And the beauty of the risk-benefit approach is that you can be comparing any two regimens and not worry about which one, is the standard of care or not. The problem with non-inferiority trials is that, you have to have the control group you might have a problem with biocreep with using the same control group. A DOR approach or a risk-benefit approach using a superiority framework actually is getting rid of that problem. I don't know if that's kind of getting at your question, but there are the field of MDR-TB, like the multi-drug resistant TB, the control group, the so-called control group, is a big question mark. We are having problems trying to run randomized trials with treating new regimens for MDR-TB precisely because of the problem of that the standard of care group is now becoming more, it's actually very much in flux because because of the dire need for a treatment for MDR-TB, actually experimental regimens are actually being used in the field now, but with things like humanitarian use, because, for example, new novel regimens like bedaquiline and delaminid are now being put out in the market, put out there in the field without a phase 3 trial, confirmatory trial of a shortened regimen. So the question of control group for certain types of TB disease, like MDR-TB disease, is very much a problem. And that's a big area of also clinical trial methodological research that we're trying to get around with. The second question, I'm forgetting what it was again.
Like vaccination?
Oh, vaccination, yes. Another good question,
How effective?
Yeah, Yeah, vaccine research is very much, we don't have a, there's no real effective vaccine actually for against prevention of TB. We have this vaccine called BCG, which is now being discussed in the field of COVID. There's actually a clinical trial that's looking at BCG vaccination, which is supposedly a TB vaccine, whether it's actually working against prevention of COVID. But BCG vaccine actually is only effective in certain kinds of TB, usually the extrapulmonary type of TB, which is very common in children, but it's not very effective in adults. So vaccine research is very, very critical. And it's actually the question of whether to think about looking at vaccine as an arm and a TB preventive therapy as another arm is also one of the question marks, because those are both preventive regimens in some way. So yeah, that's a really, really good question. I'm not sure if I have an answer to that, but the one thing for sure is that there are TB prevention therapies like INH that are working. It's just that they take a long time, nine months normally, 6 months. And now we have a 1 month regimen that's working, but there is no TB vaccine right now. And TB vaccine is supposed to be the sort of the panacea to getting rid of, the TB epidemic that's happening alongside with COVID.
Thank you.
Okay, thank you very much, Grace. We have here a comment from Edsel to Tony and Peter, very creative use of MC theory in the context of anchor theory. Also from Edsel, thanks Grace, nice applications. And there is a question here from Giselle Concepcion, our PAASE president. Iris, do you consider proteins only with high resolution structures from protein crystallography data from PDB? How about membrane bound proteins? Also for Grace, have you considered working with Philippine DOH TB teams in RITM and with TB epidemiologists in UP Manila and other TB centers? Have you accessed their quality of data they have? So we can ask Iris first to answer that, and then Grace after.
Thank you for the question. So the biology aspect of the paper was really maneuvered by our colleagues. So the one that I can answer with certainty on my end is that our source is the domain mapping of disease mutations that was a mapping from an existing database to each disease mutation by gene or protein or domain location. So in this mapping, the proteins were aligned to a database of conserved protein domains using an alignment tool. So that's as far as I know po. Pero in terms po of membrane proteins and other specific aspects of proteins, hindi ko po talaga i-claim that I'm an expert in that matter. So yun po.
Okay, Grace, on TB dots.
Yeah. I have not been in contact with folks, researchers in the Philippines. Would be very happy to have discussions. Yeah, I'm very much interested in any potential for collaboration. So anyone who wants, feel free to send an email in terms of epidemiology or clinical trials work. That would be very much of interest.
Okay. I have a quick question for Tony. Are you still awake, Tony? Other than marketing, any application you can envision for option framing?
Well, actually, it's especially with if you blend in Markov chain, wherein the options become the states, you can use it for promotion strategies, wherein you have this joint occurrences of different options. Then you can see what option gives rise to another option wherein it will trigger more purchase. So it's still along the line of marketing. The option framing, I think, is, I don't think you can cure cancer with it, but but it will give, it's more on marketing. I mean, first impression is everything. It's about packaging. It's about packaging.
But you could use it in presenting options to leaders, political leaders. They might decide to do something because of the way you put the options to them.
I think in Dr. Mariano, it's very interesting because you have this, I don't know, causality in your models. And I don't know if I can claim so much of causality with this Markov chains, because it's just a reflection of how they behave. And in fact, the Kahneman theory, anchor theory, although he won Nobel Prize for that, is also, it's hard. The quantification of this risk could still be in question, but somehow the Markov chain transition probabilities could be made use. Mm-hmm. And the use of this option framing to verify price sensitivity results can also be used in option framing. You can use that. I think so. I think you just gave me an idea, Ernil.Maybe I'll use that for checking the price sensitivity results.
You have to pay me a royalty for that.
Oh, sure. I will. I'll give you.
All right. Okay, so any other questions, comments from the participants, from the panelists? If not, great. Yeah.
I have a short question for Iris.
Iris.
Now, yeah. Now, do you have issues about dependent data that you're getting from this? Because you have these proteins, but you could have dependencies on those observations that you're going to use. So how did you deal with it? Or did you assume independence or positive quadrant dependence?
So that's one of the problems that we dealt with at the beginning. So part of the studies from Tony Kai was dependent structure. So that was part of the literature that we looked into. But for our simulation purposes, for the initial study, we did not assume dependent structure. But for the other one, we did. So we handled that caveat of the original paper. Hence, kaya po, there's a sense of nanganak yung paper because of the possible caveats that were addressed from the initial.
Yeah. Mm-hmm. Okay. Yeah.
Okay. Can we request Grace to turn on your video, and then we will ask for a souvenir photo from Pao. Pao, can you take our picture? just like in a face-to-face conference for documentation purposes.
That's a good one.
Pao, can you take our picture?
Yes, sir.
Okay.
You have to count.
Okay.
I'll join, sir.
Okay, go ahead.
1, 2.
One more.
Wait, sir. I'll just save this. Yeah. And then isa pa, sir. Okay na, sir.
Okay, so again, thank you very much, Dr. Mariano, Dr. Pena, Dr. Gauran, Dr. Maranon, and Peter, Dr. Montepiedra for a very interesting session with you this morning. Thank you for agreeing to join us at this unholy hour, especially in Sweden, Tony. Thank you very much.
Thank
Good
you very
morning
much,
again.
Ariel. Yeah.
Good to
And,
see you all. This is
Nice
nice.
meeting everyone. Yeah.
yeah.
Grace, nice seeing you again.
Yeah. Good to see you. Good to see you guys.
For the rest of the participants, PAASE, APAMS is going for the next 3 weeks. So we have 3 more weeks
3 more
for
weeks. Yeah.
APAMS. So please register ahead of time. The talks, the sessions are posted in paase.org website. So again, thank you very much. Nice seeing you all virtually at least. Sir, thank you very much.
Okay, Ernel.
Thank you.
Thanks too.
Grace, hello.
Kamusta, Grace?
Musta ka na, Grace? Nakamute ka pa.
O, pwede na magchikahan.
Hello! Nako! Oh my gosh!
Pwede ka na makipag-chat.
Ang tagal na natin.
Kailan ka pa nandiyan sa Sweden? Matagal ka na?
Naku, bago pa nag-COVID.
Nagsasalita ng Swedish.